Hi, to the second part of this session or presentation, which is about LPX. The first part, we had an overview about all the types of crossover standards, and we explained to them, and we gave some examples based on the papers that we had, which is here. And in this presentation, we are going to explain about the new approach or a new Lagrangian problem crossover in detail, which is again can be found in this paper, and the link below also you can have more details about all the other projects. Now, Lagrangian problem crossover is the new type of new type of crossover between chromosomes. Crossover standards basically have several weak and strong points, and we mentioned them. The major motivation for proving the crossover standards is to propose and demonstrate a distinctive crossover technique, which is in this paper called Lagrangian multiplier technique. And this technique is used to determine maximum or minimum of multivariable function. Now, based on LDF, LPX attempts to calculate the most appropriate offspring, which often involves taking a fairly significant step away from each parent. For example, if you look at this diagram, you have fx, which is the function that represents the equations that we have, and here you are trying to have a solution which is to get the best optimal solution could be in this surface. Okay, so you can go from here to here, or from here to here, or from there to here. So you might have several solutions, S1, S2, S3, and each one of them is fx1, x2, and x1 and x2. These are the two chromosomes we have. Now, if we look at this diagram, we could have the best solution or the optimal solutions, or the possibility that we can get the best optimal solution. Now, having said that, this red line is the gradient vector, or in other words, we can say that's the limitation, because here you can get the best. So that's the limitation. Here at the surface, you can get the best. And here in the green circle, we are putting a point that we have a gradient vector, which can be a constraint or limitation that we need to respect in our attempt. So based on the stationary point of Lagrange, to calculate the stationary point of Lagrange, given a function delta f xy 2 parameters, that equals lambda delta g xy, and the Lagrangian multiplier. This is Lagrangian multiplier. Now Lagrange equals what? Equals the equation that we have, which is mainly the two chromosomes that we have, minus the c. C here, it's a constant to represent the constraints that we need to respect in our equation. So thus gxy equals c, and if c is a constant, so Lagrange multiplier equals the equation that we have minus the the condition or the constraints that we need to respect. So from these points, it is proved that Lagrange multiplier lambda is in this equation is improved by minimizing or maximizing. So we will have offspring, which is lambda x1, x2, and we introduce alpha, which is a parameter when you introduce Lagrange. So that equation minus the alpha times the constraints. And here, more detail about the constraint can go from I equals 1 to n equals 2. Why? Because we have two solutions, x1 and x2. So then we have alpha g x1, x2. Now, as such, the LDF theorem depends on real equation samples. So to identify several local points, the theorem would be formulated using a noble crossover operator. And thus each station should generate a gene for offspring from parent chromosomes. Now, developing an alternative to conic duality theorem is called LDF. So based on this LDF, which is conic duality theorem, we are going to get our solutions. So in other words, the offspring equals the equations that we have from the two chromosomes minus the condition or the constraint that has to be respected. And the offspring one is formulated in this way: x1 minus x2 squared plus x2 minus x1 all squared. Now subject to x1, x2, which is x1 plus 2x2 minus 1, g2, x1, x2, to x1 plus x2 minus x1. And this all borrowed from the theory of conic duality theory. So these parts are brought from this conic duality theory. Now, for offspring 2, again, the same thing. x2 minus x1 in this time, and x1 minus 1, it was x2 for the first offspring. And slight change here again, x2 plus 2x1 minus 1. And you can see starting with x1 here. So that's the difference between them. And for gene 2 to x2 plus x1 minus 1. So, so to generate two offsprings, that's how we generate them. So that's the first part, and this is the constraint that has to be respected. This is the first part of the offspring 2, and this is the constraint that has to be respected. Now, imagine if we put alpha 0, then it means that the constant is 0. There is no constraints, and you have this solution. But the constraint will give you the optimal, provided that you respect it. Likewise here. So if we have this example, and we can apply this example. So we have chromosome 1, chromosome 2, two solutions, bit 1, bit 2, bit 3, bit 1, bit 2, bit 3. So we are, say for example, we take gene 1, which is x1 minus x2, and then we can have this information. Now for offspring 2, again, we can do the same thing. We can have this solution. Now, having these two genes, we can plug them into the second gene to produce the offspring 1, and also plug this result into second gene in chromosome 2 to produce offspring 2. So that's basic operation, and this is a new way of how to make a crossover, and this crossover is kind of very efficient, and it does it in a shorter time. So let's see how our results when we implemented these Lagrangian LPX crossover. So imagine for test function T as function 1, test function 3, and test function 7, and we went for 100 stochastic generation gene, and then compared to LPX to BX and SPX and Qubit. Now, we also run some statistical analysis, and we found our results are promising. So we said that 100 samples or 100 genes, we have alpha 0.2, 0.7, 0.5, 0.7, and we have TF1, TF3, TF7. You can see that LPX in maximization outperform SPX, BX, and also in all in alpha 0.7 again outperform, in alpha 0.5 and 7 also outperform. So these are higher number than sum and mean and standard deviation in BX and SPX. Likewise, exploitation and convergence evaluation results for another experiment that we have, LPX, has been assessed using the range of experiments. LPB, learner performance based algorithm, which is another algorithm that we designed. It was executed for 30 times using 80 search agents. Now, TF1, TF3, TF7, and we can see for minimization, again, LPX here outperform SPX. Time, you can see 141, 144 seconds and something. 149, 151 is higher. So the time here is shorter for LPX, and also the standard deviation much less than all SPX and BX and QubitX. So this for minimization problem, again, LPX outperformed, and you can see here the results are very good and promising, except here QubitX perform better when you have TF and alpha 0.5 and alpha 0.7. So these two bold digits are better than our LPX. Now, statistical evaluation, again, we found p-value for LPX versus SPX. In here, TF3 0.7, LPX didn't perform well, while in the rest performed well because less than 0.05. Here again, performed well here, not when the results of LPX compared with BX. So here didn't perform well. Here also didn't perform well, while here performed well here. So all in all, the contribution is very good and promising. We managed to develop or come up with a new idea, which is LPX, Lagrangian Problem Crossover, using LDF theory. And we found that this way of LPX crossover very effective, and it can find the solution, optimal solution, in less time than the other competitive standard crossover operations. Thank you very much, and to get more detail, the paper is here and the link is there. I wish you all the best, and thank you.